Okay, let's continue study the general relativity through Carroll Roseberg. Yeah, at around page 112, we use the exponential map to construct local initial equity. There is a party to find basis vector in mu for TB such that component of the metric, those of the canonical form. So here, Z Riemann numerical coordinate already know. Yeah. Cut the control in this way as known as Riemann numerical coordinate at P. We still need to verify these Riemann numerical coordinate satisfy that mu Z P Z. Yeah. And know that array in tangent space a parameter set vector of the when lambda k mu for some fixed vector k mu gets mapped to geodesic by the exponential. Therefore, in Riemann numerical coordinate, a curve x mu, x mu, curve x mu lambda with parameterization lambda is defined on the left side hand like this. Yeah, lambda. So no, k mu. Yeah. We solve the geodesic equation. Indeed, any geodesic through P maybe expressed this way for similar profit vector k mu. Therefore we have data lambda to rank differentiation lambda with respect to lambda equals 0 along any geodesic through P in this coordinate system. But by the geodesic equation, we also have do this mu sigma low P k low sigma where carrol sigma dx low d lambda p. Yeah. So since this holds for arbitrary k low, we conclude that any carrol, we conclude that k mu low sigma low p equal 0. Now parametric compatibility 0. Delta sigma z mu rho equal delta sigma z mu low sigma mu and z lambda mu sigma lambda z mu lambda sigma mu sigma mu yeah sigma mu so delta z sigma z mu where all quantities evaluated at P. We see the Riemann numerical coordinate provide the realization of the local coordinate continuum discussed in section. They are not unique. There are an infinite number of non-Riemann numerical coordinate systems in which z mu equal eta mu and delta sigma z mu. But in the expansion around P, they will differ from the Riemann numerical coordinate only at third order in X view. 3.5, the expanding universe revisit. Yeah. Let's put some of the technology we have developed to work in understanding a simple. Recall the expanding universe metric we studied in chapter 2. Yeah. Yeah. Okay, this is a expanding universe. So this metric describes a universe consisting of a flat special. This metric describes universe consisting of flat spatial sections expanding as a function of time with the relative distance between particles at fixed fixture growing proportional to the scalar factor at. Faced with the metric, if the first we do it cross as mentioned at the end of the easiest technique for doing so is actually to vary express the integral of the from 3.49 plugging in the metric and consider we have d tau dx j tau d tau. The technique is to consider variation x mu and demands that delta I vanish. We get an equation and be mindful and run for it. Its equation corresponds to a component of the equation. In the equation derived by varying with respect to the equation, the dx rho dx will be gamma mu low term. For the metric 3.72, we need to consider spiratory variation with respect to x to the t and 1 of xi. It doesn't matter which variable since the result for its special direction will be equivalent. Let's start with t plus delta t. The non-term time dependence comes from for weights to first order. At plus delta t, at plus a dash delta t, where a dot equal dA dt分dA divided dt. We therefore have dt d tau d delta t. Oh yeah, d tau dt d tau and 2a a dot delta I dxi d tau dxj delta t delta tau. dt tau dt plus a dot delta ij dxi d tau delta tau d tau. Where we have dropped a bounded term after integral part, setting the coefficient of delta t equal to 0 imply d tau Yeah, and equal to this is this part equivalent to this equation. Yeah, rho sigma d tau dx rho dx sigma d tau equals 0. Yeah, so comparison of the equation imply gamma 0 no gamma 0 equal 0. Really? I think so. 0 I think so. Gamma 0 I 0 equal gamma 0 I. Yeah, 0 I is 0. Gamma 0 ij a dot delta ij. We can repeat this procedure for a special condition. xi plus delta xi is the variation, and then delta I delta the variation is then x equal x plus delta in by the by yeah, on the other hand, yeah. Really, you can check. So yes, so yeah x I delta ij delta x j d tau. We can express d tau dA in terms of a dot by using the chain rule. Delta so the dx yeah, and yeah. How do I get there? Yeah, something like that. Okay. Okay. The setting the coefficient delta xj equal to the 0 in 3.79 implies d0 xi data with 2 power time a dot d tau dt d tau dxi equals 0. So completing the geodesic equation, we find the correspondence we must satisfy rho sigma d tau dx rho d tau dx rho. So yeah, omega I 0 equals 0. Omega I j 0, omega I 0 j, and delta ij, really? Yeah. delta ij オメガ ijk equals 0 オメガ ijk is a suffix for space, not time. So ijk maybe equal to 1, 2, or 3, not 0. Together 3 points are always correction coefficient for the metric. These are, of course, necessary both for setting the relativity. In fact, 3 points. These are the equation. Let's put these to work by solving for those followed by massless particles such as photon for the tau. With the loss, we can consider path along the excitation flow. With the loss of general, we can consider paths along with the rates x mu lambda. It's a trivia to solve the four paths of this. So using this, we have neural path minus dt0 plus azo t dx0. With the loss, we can consider path along x direction. T lambda and x lambda we make as a component 0. It's through null path. This solution could imply dx d lambda equal dt d lambda. We solve this for a tq, but here we remain more general. Also, we have chosen concept path moving in the possible x direction with determine the sign of dx d lambda. We must distinguish, however, between null path and null geometric. The latter are much more restricted class, and to show these paths are geometric, we need to solve for the coordinate t and x in terms of parameter. Let's solve for dt d lambda, which we turn out quantity which are more interesting. Plugging in the null code into the mu equals the component of the geodesic equation 3.76 and remaining to replace to we get so we get we plug this equation to this equation. So we change the parameter tau to lambda. So aa dot d lambda dt equals 0. It's straightforward to verify that this is solved by d lambda dt equal omega a omega 0. This is a equal omega 0. Omega is constant for a given at. This could be instantly integral to a to t lambda. But more interesting, it's considered the energy of the photon as it will be measured by a co-moving observer, a one fixed special who would have velocity. Co-moving observer. On photon. Don't get it tricky to think that time like the probability of a particle at rest will equal. We need to satisfy the normalization function, which is less frame ui equals 0 imply ui u0 and using p mu x mu e minus p mu u mu, yeah, and so this is dx0 d lambda u0 minus c00, and dx0 lambda is p mu p0. So yeah, this is a equation u0 a omega 0 omega 0 with the y is chosen for constant of proportionality in omega 0 is the frequency of photon when a equal 1. But we think frequency omega 0. Hence because equal rates omega equal h omega, we are using it. Yeah. We have uncovered a profound phenomenon, the cosmological relativity. We have uncovered profound phenomenon, the profound cosmological relativity. A photon emitted with energy E1 at a scalar factor A1 and observed with it at scale factor it will have A2 E1 equal A1 A2. Omega 0 is a constant, so yeah. This is called a redshift because the wavelength of photon is inversely proportional to the frequency, and in an expanding universe, the wavelengths grow with time. As a practical matter, this provides an easy way to measure the change in the scale factor between users, and also serve as a proxy for distance. Since the universe has more monotonically expanding, a greater redshift implies greater distance. In conventional notation, the amount of redshift is denoted by I think you know this z. Omega 2 is observed frequency. Yeah, omega 1 is original frequency when emitted, which means when emitted. So yeah, this is a redshift factor. I think you know. So the vanishes if there has been no expansion for if the emitter and observer are so close, there hasn't been enough time for the universe to appear appreciably expand. There hasn't been enough time for, as mentioned in section 3.3, it's not depressive. This is not depressive. This was another interpretation to refer to the velocity of the receding galaxy. Now we can understand this statement quantitatively. You might imagine that as far as behavior of emitted photon is concerned, there is a little difference between two galaxies physically moving apart in flat space-time, two galaxies at fixed core moving coordinate in expansive space. But let's consider a specific Yes, but the educational example start with a flat space and imagine the two are inside not moving apart. But at rest in some global inertia, one emitter photon towards the other while the photon is traveling. We quickly move the two galaxies apart until they are twice their original separation. Then leave them stationary at the distance, and then the photon absorbed by the second galaxy. Clearly, there will be no Doppler shift since the galaxies were at rest both emission and absorption. Now, consider the analogous phenomena in expansive spacetime with the galaxy's star graphics. We begin with a scale factor constant. So, yeah, if this, consider, I say, in summary, Duncan experiment, if this is on the flat space, which means at equal 1 at any time t, the process even to galaxy moving apart from each other, they receive a frequency. They receive frequency as the same of when they emitted from other galaxy. So there are no Doppler shift. One galaxy emits a photon, but other case, if the galaxy is expand with expanding universe, which means in this case at equal at increase as t pass, as t goes, time pass. We imagine drawing the photogeneration to image flat experiment. The scale factor is twice its result, and then stop experiment before it's absorbed. In this case, there certainly will be redshift despite the fact that there was no relative motion or ill-defined concept in any case. Until they are at rest, then they leave the step center at the in this case they stop if you get. And second case, at is moved, but when they get photon from other galaxy, they stop. For easy Gedanke experiment, in this case, their Saturn will be red, but they will be redshift. As is observed emission, the photon level will have double as a scale factor. Doubled, so we observe the redshift as well. This demonstrates the concept distinction between the cosmological redshift and the conventional Doppler effect. Cosmological redshift. So we say we've found the concept of cosmological redshift differing from Doppler effect. Beyond the geodesic equation, covariant derivative will play a role in generating law of physics from the flat space-time special to the curved geometry of general relativity, as we'll discuss in more detail in the next chapter. A simple rule of thumb is simple to replace all partial derivative by and all appearance of the flat spacetime metric eta mu by the curved geometry. For example, the energy moment conservation special where T mu is one equation of special relativity T mu, and where T mu nu is the tensor become eta mu T mu become in general relativity. We typically model the matter thing with the inverse of the perfect flight. The quantum energy moment that comes from generating to curved space-time T mu. Oh, sorry. We have time, so let's go to the week 2.